Hello, everyone. A very happy Tuesday and welcome back to our ARM Tech Talk series. This is the place for the latest and greatest trends, technologies, and best practices from ARM and our ecosystem partners. And I'm super excited to be joined today by Jim and Mark from Carnegie Mellon University and ARM, respectively, who are going to talk to you a bit about how you can build an edge platform with your own private mobile network. It's a really exciting tech talk we've got lined up for you today. We do these every week at the same time, 4 p.m. UK, 8 a.m. Pacific time. So it's great you could join us this week if it's your morning, your evening, if you're in the car, if you're sat at your desk with a cup of coffee, wherever you're joining us from. Great to have you. As you may have attended one of these talks before, I've got a couple of housekeeping items I'm going to go through first before we get to the meat of today's talk, which is why you joined today. So let's get through those as quick as we can. But just to tell you how you can get involved in today's conversation, Jim, if you could go to the next slide, please, that would be amazing. You can, of course, use a hashtag ARM Tech Talks to engage with us on any of the social media platforms out there. We have done 75 of these tech talks now, so all of the recordings are available on our ARM YouTube channel. Just head to youtube.com/ARM. You can check out all the great tech talks there that we have done with our partners, and all of our upcoming talks on arm.com/tech talks, so do check those out. As a sneak peek of what's coming up on the next slide, you can see that we've got Synopsys talking next week on the 10th of October, talking about their collaboration for faster bring up of next generation SoCs and multi-die designs. If that sounds of interest, go and sign up now to make sure you get your space secured. And then we're just about to get our 24th of October talk live from ARM talking about smart vision, which is really, really exciting as well. So that's enough from me. Before I hand over to Jim from Carnegie Mellon University and Mark from ARM, just a reminder, please get your questions in as the talk goes on in the Q&A box at the bottom of the in the Zoom menu bar. If you haven't used Zoom before, it's just check out the Q&A box at the bottom, and we'll get to those at the end. So Jim, Mark, thank you so much for joining us for today's ARM Tech Talk. It's really great you can join us. Super excited to hear what you've got to talk about today. I'm going to hand over to you both now, and I think, Mark, you're up first. So please take it away with today's ARM Tech Talk.
Thanks, Tobias, and thanks everyone for joining us on this talk on the just-in-time Cloudlet. Today we'll share the technical details that make up this project, and we'll talk a little bit about the journey that made it possible, which includes a combination of precise development efforts in open source projects, the general advancements of hardware making this possible, and then the need to pull all this together to create a solution platform that is replicable, by all of you on the line today. ARM has been supporting the work of the Living Edge Lab at CMU for a number of years, and our engagements with the universities are a little unique when you compare that to the commercial engagements that we have with our customers. In this case, CMU picks the project and drives the vision forward. So it's their vision, their project, and we have regular syncs together to kind of walk through the journey, right? Making sure that any roadblocks that come up, we find ways to overcome them. And ARM really represents the industry and pulls in players from our ecosystem to join and help out. So we encourage academia industry partnership as a great way to advance projects that have potential to be disruptive, but are often also large or long-term projects. So one of the unique aspects of this engagement is the university environment provides a unique environment that allows the team to focus on the technology and the problem at hand with little distraction. And that's what makes this possible. So at this point, I'll invite Jim to kick off this project and tell us more about what is the Just-in-Time Cloudlet.
Yeah, thanks very much, Mark. And I just want to say at the beginning here, it's been an absolute pleasure working with you, Mark, and with the rest of the ARM team over the course of I guess at least 2 or 3 years now. We've been working together in this project probably about a year or so now. So it's been quite exciting. I want to start with just a little bit of grounding, just for some terminology that we're going to use during the course of the talk, so I don't have any confusion to begin with. First of all, the Living Edge Lab is one of the premier research organizations around the world in edge computing. That's pretty much our sole focus in the work that we do. So we've been around a long time. Actually, the founder of the lab, Professor Satya, is one of the founders of edge computing historically, and he coined a term about almost 15 years ago now called a cloudlet, which is really the foundation of edge computing. It is putting world-class computing, close to where end devices and their users may be, and what we now refer to as at the edge. And the reasons for doing this are really because of the value that location close to the user actually brings the application that the user is trying to use. So there's advantages in terms of bandwidth. There's advantages particularly in the form of low latency, round trip times getting through networks and back. There can be privacy advantages when you have data that's created at the edge that can be preserved at the edge. And if the cloud or the network goes away, you can continue to operate without having any loss of service to the end users. And what we refer to as an edge native application is one that is custom designed to take advantage of one or more of these attributes going forward. So that's just a little grounding. Now I want to get into the actual meat of the project itself. So when we started talking about this concept, we realized that there were a number of use cases where the users may not be easily able to connect up to the cloud. There may be a poor mobile network connectivity nearby. There may be no backhaul from that local site to the cloud where services typically get deployed. And there may not have been any edge computing deployed at that location to give those low latency and other benefits to the application itself. These applications can use all sorts of devices: mobile phones, drones, cameras, wearable devices, and anything else that can hook up to a network. And we think of that just-in-time cloudlet as something like an edge computing hotspot. You may have no connectivity whatsoever in a particular location. Can you drop in the computing close by and get up and running within a few minutes? And it's easier to think about this concept in the context of specific use cases. This is just one of the many that we see. Search and rescue cases. So imagine in the mountain, there's a lost hiker up in the woods, and a team is dispatched up into this remote area to be able to search for that lost hiker, find them, and send crews up to locate them. This could be very well a situation where there's no connectivity, no mobile network coverage in the area, no backhaul from the area to the cloud, and no local computing resources. You have to haul it all up with you. And this is the case that we chose to focus on, not just because we think there's a lot of use cases that look similar to this, from military kinds of operations, bridge inspections and infrastructure inspection kinds of applications, even entertainment, sort of remote wilderness kinds of events that may happen that need to provide sort of some level of connectivity like this. So there are quite a few use cases for it, but we also thought that this looked like one of the more extreme integration cases for putting together a solution that would provide edge computing in areas where there was no edge computing today. Edge computing, as it rolls out, is, it can be a capital intensive kind of operation where you have to deploy first the mobile networks and then the computing devices around in regions. And so going and doing a mass deployment of edge computing could be quite expensive. This is a way to do it in a very self-contained, targeted point implementation. So we felt that this was well worth exploring. to see whether or not we could build a fully integrated solution like this that was built off of standard kinds of building blocks, both from a hardware and software perspective. As a lab, we're very focused on open source activities. We believe everything that we do from a research perspective should be replicable by others. And in a modern world, that's pretty much only accomplished through use of standard off-the-shelf building blocks and open source software. So that's a primary focus for us as a team. So we defined a set of requirements for the just-in-time Cloudlet architecture and a prototype that we built that I'll talk about more in a minute, to be able to sort of build a proof of concept around the whole just-in-time Cloudlet solution. The first main criteria was cloud native at the edge. This has to be built on a modern cloud-oriented architecture, or what we think of as cloud native at the edge, mostly architected as containerized microservices running on a fully integrated Kubernetes-based environment. It should be no heavier than a typical normal check bag, or as my boss keeps saying, I want it to go in the overhead bin. It should fit into the weight and space of a normal check bag so that those search and rescue teams that are jetting to the scene to find the hiker can get it into the airplane without any having to have any shipping issues. Should run on household power. I shouldn't need any special power equipment to run it. It should be able to be deployed and up and running, including the entire mobile network that goes with it, within under 3 hours. Many of the applications that we see here are computer vision and AI types of applications. And so it really needs to have accelerated computing and oftentimes graphics capabilities. So it has to be able to support a GPU. It should work with no or very, very limited backhaul capability. One of the things that we've learned through this is that there are some features that really should have even a small narrowband backhaul connection that could be satisfied by a satellite connection there on site, but doesn't have the bandwidth or the low latency that's required to support a number of these applications. From a software perspective, everything should be open source. Anything that isn't open source isn't replicable, but also for people who may want to go and build solutions on it, open source provides a great way for them to get going very, very quickly. From a hardware perspective, everything should be commercial off-the-shelf equipment, things that are available widely and can be purchased from multiple suppliers to serve the need, rather than just being purpose-built hardware for a particular solution. From a security and privacy perspective, these sorts of use cases have some unique requirements in terms of both supply chain security and data protection, and on site. These are typically not going to be deployed in an environment with physical security. It's not like a data center where it can be locked down behind berms and moats without access to anybody who's not authorized. It could be out in the wild someplace, so it needs particular data protection and security considerations. So let me talk for a minute about cloud native at the edge. Over the past 20 or so years, a number of technologies have emerged mostly from the cloud space that are open source projects that replicate a lot of what it takes to build a complete continuous integration, continuous development environment, and be able to operate a solution based almost entirely on open source, and certainly based on the idea of interconnected microservices that communicate together through a common platform. And so we adopted this paradigm, particularly focused on the lower layers of the stack, to assure that we could have this sort of common platform that could be widely deployed by anyone using relatively common tools. And so the foundation of this architecture is using these capabilities to be able to build a complete solution. And with that, I'm gonna, actually I have one more slide before I turn back over to Mark, sorry. The other concept that I want people to be familiar with, and I don't know the background of everybody on the call, but There, within the telco and cloud space, there's what I think of, there's a little bit of a failure to communicate between the two sides of the house. And I'll focus this on ETSI MAC, or multi-access edge computing reference architecture from ETSI. But it's a common problem that we're seeing among people who are either coming from the telco space or the cloud space. The telco space thinks about edge computing as predominantly focused on the network. It's really about building a modern network on a software-defined infrastructure to support what are basically virtual network functions or capabilities that the network needs to provide to users. On the other hand, the cloud world tends to think about user apps, augmented reality or computer vision or other sorts of applications, IoT style applications that should live close to where the user is to give them a better user experience. And the stacks for these two, even though they may architecturally be similar, are generally treated as separate kinds of platforms. So you would have your network infrastructure and you would have your application infrastructure as separate. We wanted to break this concept. By the way, there's some good reasons for keeping them separate, for security, performance, and isolation between users and critical network functions. So it's not as if this is a naive way to do things, but we wanted to push the boundary of bringing these two stacks together and running everything on top of a single host system. So the just-in-time Cloudlet takes a view that says we're going to integrate all of this together. And that brings us to some of the key enablers that are necessary for us to actually build something around this concept. So now I'll turn it over to you, Mark, to pick up the next couple.
Thanks, Jim. So as Jim was just saying, the marriage of cloud native development and mobile edge platform needed to run in a single box. We wanted something that was efficient, portable, and yet powerful, right? Because you need a number of cores to be able to run all these workloads and to be able to do some of the computation that Jim was mentioning in the previous slides. So we picked the Ampere developer platform. It's the one on the left here in the picture. It supports PCIe interfaces times 16 lanes. So that's big enough to support GPU cards, to give you access to some of the accelerators that are required to do some of the AI and ML processing that you may need at the edge. So that was something we wanted to check the box on. We wanted to make sure this box was affordable and accessible. And if you follow the link below this Ampere AD-Link development platform, you can find it available on the IPI website. And I believe it is in a range of $2,600 or starts at $2,600. So for a 32 core, powerful server in a box with liquid cooling and the ability to add a number of PCIe cards, comes in at a good price point. So we feel like that's an accessible box. Now, recently, Hawkeye and Marvell have teamed up to create a smaller developer platform with 24 cores, also with a number of PCIe ports. We are just in the process of bringing this system up, and we're going to explore, transporting the platform from the Ampere developer platform over to the Marvell box to create a smaller solution. So this server is a bit smaller, less power, and may be able to open up use cases where size is an additional limitation. Of course, Jim mentioned this early on. We wanted to be able to plug this into a general power outlet. That includes a generator. So if you're out in the wilderness and you need to run this system, a standard 1500 watt generator with a 15 amp output at 110 volts will run any one of these servers, with all the equipment that we've described here. So that makes it very portable. And then on the radio side, again, we wanted something that was accessible, standard, off the shelf. And we were able to find radios from Baycell and Sercom that met that requirement. And if you are looking for creating these solutions or replicating this design, I recommend you get in contact with these two companies. They have systems that are available and they are qualified for the CBRS band. And they've also been validated with the Magma stack. So we're going to talk about that in the next slide, some of the details that are required on the software side. But that was the hardware. Those are the hardware elements that we needed to pull together for this. All right, now looking at the software side and what we've needed to pull this together. So Magma is a project that sits under the CNCF, Cloud Native Computing Foundation. It's an open source project. It was a donation from the team at Meta. They created this initiative. They donated it to the Linux Foundation. ARM joined this project. And at the time, we were really focused on making it cloud native. So we invested energy in taking the Magma stack in its original instantiation and then modularizing it and containerizing it. And that allowed for a networking core that can now sit a lot closer to your software stack and can be managed by an environment that is the same, right? You can orchestrate it from Kubernetes. When you look at the details of the Magma stack, so these are modular blocks. At the bottom here, you can see the access network, which if you look at the little antenna there, you can see LTE, 5G, and Wi-Fi. So by interchanging that block, right? You pick the block that matches your radio, you can connect to any one of these technologies with no impact above that, that block. It really isolates it, which makes it modular. There's also support for a GPRS tunneling protocol. And with the federated gateway module, you have the option to connect into a backhaul or an operator's network. And that'll help facilitate core functions such as authentication, policy enforcement, or managing a data plane. So again, you can see that this is modular blocks. You can choose to connect with the federated gateway or not. You can run this standalone. And that's the beauty of the Magma project. It's flexible and it's accessible, and something that was used to create this solution. Now, in order to create this private 5G or LTE network, we needed a communication band. And in the United States, we are blessed with a CBRS band, which stands for Citizen Broadband Radio Service. And that's essentially an open environment where you can communicate between devices, using a standard radio, same as what you have in your mobile device or in any device that connects to 5G or LTE. All that you need is for that UE device or the radio to be validated on this channel. So it's not like you need a brand new hardware that just communicates on CBRS. You can use standard off-the-shelf radios that just have that checkbox, qualified for FCC to run in the CBRS band, and then you're up and running. And as we showed in the previous slide, there are radios available. There's also end devices that you can use and connect to this spectrum. So that's a communication channel that we used to create this wireless network in the just-in-time Cloudlet. I'll pass it back now to Jim to show us how we pulled all this together to create a proof concept.
Okay, yeah. So let's talk a little bit about what we built. So taking that ARM developer platform that Mark showed on the previous slide, we built on top of it an Ubuntu 2004 with Kubernetes stack as the base overall platform. And on that same server, we deployed the Magma gateway, and we deployed a couple of our own edge native applications developed here at the Living Edge Lab, Open Scout, which is a computer vision object detection application, and Open Artist, which is an augmented reality style transfer based application that sort of it translates your incoming camera feed into the style of a famous artist. So if you want to see your face in Van Gogh style, you can do that. And then finally, because many of these use cases involve collaboration, interactive collaboration between an operator on site and other, in my search and rescue example, first responders that are going out for the rescue, we added WebRTC as a video conferencing capability, much like you would see with Zoom, except entirely contained within the box in order to support the users that are on site, even though there may not be backhaul associated with it. We use the BiCell's eNode B. That's a 4G LTE device. We built this all around 4G LTE to start with, primarily because the components that we used here, including the BiCell's eNode B and Magma, are also the components that we're using in our on-campus private LTE research network that we built out a couple of years ago. So these were all proven components for us, and it made the job of integration a little bit more straightforward. We are now in the process of migrating this to 5G. With 5G, we expect to get substantially better latency and hopefully a little less power consumption on the whole platform to support the use cases that we're looking at. But right now, this is a 4G LTE solution. Hopefully, in the next month or so, it'll be up in 5G as well. On the right-hand side here, you can see the physical footprint of the entire solution. The desktop style server down there at the bottom, which is the Ampere box, as well as a management console laptop, which also runs the Magma orchestrator, plus a little bit of switching and routing gear there to basically connect all these boxes together. So that's what it looks like from an architectural implementation perspective. Let's see how we did against our results. So weight and space, this is probably the one that we're furthest from meeting at the moment. I think there's a 50-pound limit for normal size check baggage on US airlines. We're at 83 pounds right now. That includes a 36-pound hardened case to put it all in. So we're almost there without the case, but it's a little bit heavier than we would like and a little bit bigger than we would like. So those smaller form factors like that Marvell box are appealing to us to be able to see if we can shrink this down even further. Power, we met no real issues there. Everything up and running with the GPU functionality we have in it today is fine. We actually took one of those boxes though and put in a 600-watt GPU just to see if it would support it and for some of our future work, and it did continue to run with the 600-watt GPU in there. The deployment time for this, we are still doing some of the preliminary testing, and we'll talk a little bit about our trip to OCP in a couple of weeks, the Open Compute Platform Conference. So that'll give us a nice end-to-end test of bringing up this solution from scratch on site. But a test run the other day was up and running in about an hour and a half. So no issues there. We talked about the GPU a little bit. One of the big requirements was to work with no or narrowband backhaul. And this in particular is important because many modern services, many modern applications depend on some level of cloud services capability to access data or to access functionality further back in the cloud. So being able to run the whole thing with the applications in it was very important to it. So we met the no backhaul for all intents and purposes. However, the CBRS band has something called spectrum allocation service, I think, or something. Anyway, it's a service that you have to subscribe to in order to make sure that your radios are not interfering with anybody else on the same band, and so that you need a low bandwidth backhaul connection in order to support that, which could be met easily with satellite kinds of capabilities. Everything is open source except for the few boxes like the switch, the router, and the eNode B, which are closed source systems. We can't go in and program them other than through the maintenance console. Everything COTS, for all intents and purposes, everything in this solution is commercial off the shelf, including the eNode B. However, because eNode Bs are, particularly for the CBRS band, are not widespread. There are a limited number of vendors providing them. We labeled them as not COTS today, but as that market scales up, those will become much more standard high volume kinds of products. And we simply just have not had time to look at the security and data protection requirements. We did do a first pass through this and looked at the particularly supply chain and physical access kinds of requirements that are associated with it. The other thing that I don't provide any specific numbers for, but will appear in our upcoming tech report, are about the application performance. The only thing I will say that those applications, OpenArtist and OpenScout, we have deployed in disaggregated solutions in a number of different places. And our main requirement was to be able to meet the same performance level that we would see when they're in a system that is not so tightly integrated as this one is. And we did achieve that, but the detailed numbers will be in that tech report. And so next steps, I mentioned 5G. We want to move to 5G with O-RAN, the other form factors. We are building out a couple example applications that are a little more realistic. One is a search and rescue application. These are, again, demo applications, not real deployable ones, and an entertainment, backcountry entertainment example. We're also, to make this easy, this took a lot of very motivated engineering to get this solution to work in the first place, and we're looking to automate that with a deployment recipe in the next month or so. And then we're starting discussions with interested industry players to figure out how to get this entire concept to market and to be a scalable solution. Not coming from Carnegie Mellon, but coming from commercial players that want to make a product out of it. I mentioned the tech report that should be out within the next week, and hopefully by the time you get the recording of this and the slides that go with this, we'll have the web link to access the tech report for us. Finally, we'll be at the ARM booth at the Open Compute Platform Summit in 2 weeks. So please check us out there. We'll have the system up for demoing there, and I'll be there to talk to you about it as well, Mark. If you want to really get started here, I would start checking out Magma and building a private lab environment to test Magma with, and we can support you if you have questions about, what can I run on it from an application perspective. Finally, just a few references. Some of these were scattered through the presentation, but if you really want to get more information on it, these are good places for you to do it. And again, this will be updated with the tech report when it becomes available. So with that, I'm finished, and back to you, Tobias.
Amazing. Thank you, Jim and Mark. A fantastic presentation. Really, really great stuff. And I've learned a lot during the presentation. I've got a couple of questions for you as well. And audience, it's now time for you to get your questions in as well for these guys. So do get this in. We've got a few minutes now, a bit of time now for questions. So yeah, plenty of time for you guys to get your questions in to our presenters. So I want to touch on the network side first. You mentioned the CBRS band. How would that work outside? How would this work outside the US where there is no CBRS?
Yeah, that's a great question. In the US we have CBRS. A couple countries that we have found are starting to offer different but similar licensing regimes. Both Canada and Germany have announced licensing schemes that would allow you to deploy your own private network on if you're not a telco operator. And so those countries, and hopefully more in the future, will offer those. If you want to just get started in someplace that doesn't have it, many countries have a experimental license model that would let you do some level of testing and prototyping. It is challenging for going to large scale production in those environments. And then the other option certainly is partnering with your local telecom operator to see if they would be willing to let you share spectrum in some environments. But it is challenging. The reason we particularly called out CBRS as an enabler is because it is such an enabler for use cases like this, and hopefully more countries will see that as an opportunity to get new innovative solutions out.
Yeah, And to add to that, if you are interested in getting the software off the ground, start building this out, you have the option of plugging in the Wi-Fi interface to start with, right? So Magma, with its modular blocks, you can just take the block that connects to Wi-Fi, plug that in, and then once you're ready to get connectivity over LTE or 5G, you just swap that block off. And that's part of the reason why the integration or the migration from LTE to 5G is going to be pretty straightforward. We just need to make sure the hardware and the Magma core are compatible, but it's really just one modular block that's affected. Everything else on top of this software stack is not affected by the radio interface.
Thank you both. And you mentioned about 5G there, right? I guess there's kind of a two-part question here. Why didn't you start with 5G itself? And actually, how do you expect things to improve with 5G?
Well, we did start with 5G because, frankly, we already had it working. We had a lot of the technologies working with 4G LTE, and it was a much faster path to get started with that. When we started this project, for example, the Magma 5G implementation was just coming out. This was just a little over a year ago, and so we didn't want to necessarily put all of our efforts into something that we hadn't proven before. So we just decided to wait. It was always our intention that 5G would be better for us, and how better. So particularly end-to-end latency right now in the network that we have with this, we're seeing actually 20 milliseconds round trip times, which is really quite good for LTE. We typically, even in our own private network, we would see a 30 millisecond round trip time. And commercial ones are usually somewhere between 50 and 100 millisecond round. So we're seeing better performance even on LTE. When we go to 5G, we expect to cut that close to in half in order to really drop that down. And that's important because for a lot of the applications, particularly those that have tight user interaction requirements, the difference between 20 milliseconds and 10 milliseconds from a human perception perspective is very, very large. It looks much more normal at 10 than it does at 20. So for us, that's a quantum leap in kind of the kinds of applications that are possible in this environment.
And hopefully at lower power, right, Jim?
And hopefully at lower power, yes. The other thing, just architecturally, 5G adds some interesting capabilities as well with the architecture for it and the emergence of some of the more software-oriented technologies that come with that are going on in parallel, like, for example, the SD-RAN work, software-defined RAN work. We're hoping we can actually push more and more of the RAN functionality into the platform as well, and even reduce the cost and footprint of the RAN itself somewhat with 5G. Those capabilities are not available in 4G.
It might be worth clarifying, right? When we buy these radios off the shelf, they come with their own RAN.
Yes.
It comes as a package. And that's why you can really just pick it up and connect it to the Magma core. But what Jim is describing here is taking that one step further and decoupling the software that runs the radio from the radio itself and having that package in a cloud native way as well.
Gotcha. Thank you both. Really, really comprehensive answer. Thank you. I've got one or two more questions, but audience, this is your time to get yours in as well. I see one that's just come in, which we'll get to in just a second, but we've got a bit of time for questions. So you've talked a bit more about, you talked a bit just before we got to this slide actually about how we would make this a commercial solution. Is there anything else you'd like to add to that in terms of how would you make this commercially viable product, a commercial solution? What's next there, right? We'd love to hear a bit more on that.
So I'll let you pick that one up first, Mark.
Yeah, sounds good, Jim. Maybe a few things to bring up because I like this question. I think in the case of research, having a goal of changing lives or deploying in real life scenarios is important. When you look at the technology that we're using to create this solution, the Magma core, for instance, has been deployed in production. It's used in Africa in environments where there is no connectivity. They open up a small cell, they allow the people in the village to connect to this network with standard mobile devices, and then they have a backhaul, right, connecting to a satellite feed. And that's all powered by the Magma core. There's also companies in the States that are deploying extender boxes to provide connectivity as an extension of a intranet. You know, if you go into an apartment building and you need to provide more bandwidth than what is capable, you know, on the feed in from your copper line, you can extend and create a network within that building with the help of Magma. And there are companies that Connect 5G is one that comes to mind that has created solutions that are commercially available. Now, when you think about the work we're doing in this project, we're really, you know, pushing the envelope on what is possible, right? We have this idea of this concept, and you know, the CMU lab, you know, really invested in this space at a time when the technology was not available. So if you think back at when we kicked off this project, Jim, we had a number of issues, right? It was a page full of hurdles that were, you know, barriers to this being possible. Those have all been checked off, right? We now have a concept, a platform that is achievable. And at this point, as you see here in the ongoing and planned section here, we are now in discussions with industry in general, looking for ways to, you know, educate and show how this concept can help, you know, make life a little bit easier for everybody out in the market. In any use cases that these players come up with, you know, we're open to have those discussions. In fact, we have private workshops lined up where we invite these industrial players to join us, and we talk through a, you know, open forum around the concept that's being presented here today.
Brilliant. Thank you both. Let's get to the question that's just come in the Q&A box here. So will there be a blog or some kind of collateral externally that has information for creating an end-to-end solution, front haul and back haul, with hardware and software specs?
Wow, I think I appreciate you asking that question, because I have a great answer for that. In fact, that's what's in the tech report. The tech report is a reference architecture for what we built for this solution, and the appendix to that tech report includes this, I'll call it the bill of materials. It's not quite orderable, but it is all the component technologies and the versions and capabilities that they support. So that will be coming out again, I think hopefully by the end of this week, if not the end of next week. And that's a great source material for how to go out, how to build it. We didn't try to replicate, you know, so a lot of the network piece of that question is something that Magma supports. And so we didn't try to replicate all the information that Magma and the Magma project provides in order to be able to configure networks and set them up and get, you know, the user equipment to connect to them. But that material is available through the Magma community. Now, with respect to a blog, yes, well, we're going to put together a blog before OCP that will sort of tie all of these pieces together and point you to, you know, back to this webinar if you haven't been here, but also to where the tech reports are and other information that will be useful, and that will be more of a summary of all the information that's out there. Anything to add to that, Mark?
No, that's great. You hit it.
Really comprehensive. So I hope that answers your question. Apologies, I've clicked answer before I saw, and I want to make sure I pronounce this correct. I think it's Vinud who asked that question. So thank you for that. Thank you for that question. So just before we wrap on, chance for one last question to come in, Jim, Mark, is there any final things you'd like to add today based off of the questions that have been asked or topics you've covered? Is there anything final you'd like to say to the audience before we get to one final question or wrap up?
Just one quick comment. You know, this is early days for this solution set, and it will be very use case driven. And part of the reason that we're so excited about this is because we've been working on edge computing for a very long time, and it's been very slow adoption in terms of, you know, people rolling out large scale infrastructures to support it. And this project kind of breaks that log jam of waiting for customers for applications and waiting for infrastructure that that lets you get started and deliver an application without waiting for a massive infrastructure deployment. So we're very excited that this will be, an enabler, not just of the particular use cases we're looking at, but also edge computing in general. And so the more proof points that are out around this sort of a concept, the more motivation there is for even broader deployment of edge computing.
Yep. Yeah, and
Mark,
I guess
what
all I could add to that is reach out to us if you have a use case, right? We're in the process of defining what the next steps are in this project. You can see some of the planned work, but we're very much interested in hearing about use cases that are interesting to you. So reach out to us, come find us at OCP, or you can reach out to Jim and I directly. You can join us in the Magma community as well. You'll find us in all those places.
Yeah, definitely go and check them out at OCP. It's going to be a great event and super excited to have you guys there. One final quick question before we wrap up has come in. Was open air interface considered instead of Magma?
Not by us. We were, very focused on Magma from the beginning, in part because of the relationship we had with Meta and also with ARM. And their support for not just the software itself, but the support for having us build something on top of it. And so we have found, Magma has been a great tool for us, and it made it possible for us to be independent of other vendors that required, different pieces. I know Open Air Interface might have provided some of that as well, but the support that we had for Magma itself was very good. Magma also is designed around that same paradigm of microservices, running on Kubernetes, and so it was very close synergy to our operating model anyway.
Brilliant. Thank you for that. I think if there's no other questions, then we'll wrap up today's Tech Talk. So thank you so much for your great questions. We're really, really excited to have Mark and Jim present today, and you've had some great questions for them. So thank you for that. And Mark, Jim, thank you for an awesome presentation. The slides and recording will go up as soon as we can, straight after this talk. We will check those out, and of course, go and see them at OCP in 2 weeks' time. So not that long at all. So Jim, Mark, thanks so much again for a great presentation today. Audience, thanks for your great questions, and we look forward to seeing you same time next week for another ARM Tech Talks. This one will be the next one will be from Synopsys, so do go and register for that one immediately. Just head to arm.com/tech talks to do so. Jim, Mark, final words. Thank you so much, and we hope to have you back soon.
All right,
thank you, Tobias. Appreciate it. Thank you for everybody.